the form of a traveling sine wave is y of xt equals a sine of omega t minus kx. Now what does this mean? Well, if we first hold t constant, then this omega t will be a constant term. And if you know about the graph of a sine function, we see that this constant term will just involve a shift of the function, the negative kx. Well, you know, that's we're essentially going to have a times the sine of negative kx, and then some kind of a phase shift according to omega t, which means you'll have a sine wave. Now the sine wave starts here at 0, and this one is shifted where it starts here. So it's been shifted over to the right a little bit because of omega t. Whatever constant t is going to determine how far this thing has shifted. Now we essentially have a times the sine of kx, but shifted over a little bit. It's actually a times the sine of negative kx, which really means it's kind of negative a sine of kx, but that's not going to make a lot of difference to what we're going to say right here. That'll make a difference a little bit later, and we'll see what that does. Okay, the wavelength, well, to go from peak to peak by changing x, what has to happen? Kx has to change by 2 pi. Because, of course, going from peak to peak, the argument of the sine function changes by 2 pi. So we say that between here and here over the wavelength, kx changes by 2 pi. So that if lambda stands for the wavelength, k times that change lambda has to equal 2 pi, which means that lambda is going to be 2 pi over k. So you should understand that argument. We should see then that the wavelength is lambda equals 2 pi over k, because that much difference will take kx through a difference of 2 pi. This is a snapshot of the wave at some constant time t. Now, as t changes, omega t is going to change, which means that the shift of the graph is going to change. So perhaps the graph will shift over this way more and more as t increases. Perhaps the graph will shift over this way as t increases. We'll see later how that works. But you should understand that this snapshot is going to change with changing t by either moving progressively to the right or to the left, because the phase shift is going to keep increasing. Now, if we take a point on the graph, that is, let x equal constant. So if x is constant, we're talking about a point on the wave. We can graph the displacement of that point, y, versus clock time t. So if there's a point on the wave, well, if there's a sine wave coming by, that point's going to be going up and down in simple harmonic motion. And this is a time graph of that motion. Again, depending on what x is, this thing's going to be phase shifted to some point. And it could be to any point. There's just a small phase shift here, maybe. The distance between peaks of this graph corresponds to the period of the oscillation, since this is a displacement versus time graph now. It's omega t that's changing, not kx. So what has to happen to drive us through a period at constant x? Well, omega t has to change by 2 pi, so that omega t equals 2 pi. Big T stands for the period, little t stands for clock time. So omega times clock time changes by 2 pi, so that omega times the period has to equal 2 pi, and the period then is 2 pi over omega, as we see here. Now again, this is the period of motion of a point on the traveling wave. To see how this wave travels, we look at the function y equals a sine of quantity omega t minus kx as a kx graph that's shifted by omega over k times t. Now let's see what that means. Okay, in the first place, a sine of omega t minus kx, we can rearrange what's in here. First of all, we're going to take the negative of what's in here. We're going to say we have negative a times the sine of well, it'll be kx minus omega t. But we're going to factor the k out of all expressions, and we get k times the quantity x minus omega over kt. This is a graph of y equals negative a sine of kx shifted to the right by omega over k times t. So that this omega over k times t is the shift of the graph. We can express this omega over k as just the velocity, because if the graph is shifting omega over k times t in a time t, then the velocity has to be omega over k. This is how fast the graph is moving to the right. So we have negative a times the sine of k times the quantity x minus vt. And we have a comment. At clock time t, the graph is shifted vt units to the right. That's real consistent with our definition of velocity. Now, of course, you have to understand how a graph shifts, how replacing x by x minus vt shifts the graph. That's a pre-calculus concept. You might have to review that. We don't have time here to go into the details of that concept. But that's why the graph shifts to the right, and this is why then this a sine of omega t minus kx is moving to the right. Now, if we had a times the sine of omega t plus kx, what would that be? Well, we could write that as a times the sine of the quantity k times the quantity x plus vt. This means that we have x minus a quantity where the quantity is minus vt, shifting to the left by vt. So the wave is moving to the left, and the wave velocity will be negative. In a minute, we'll talk about where the wave equation comes from.